All right, let's start. Good morning. Okay, let's see how my microphone does today. So far, so good. Okay, so we're going to be looking at section 4.5. And the topic is curve sketching. So there's nothing really new here. We're just going to use what we have learned about the shapes and the derivatives and all that stuff, put it all together to try to come up with reasonable sketches of reasonably complicated graphs. Plus other information to sketch. And it's actually a very, very good way to review everything we have seen so far. The first derivative test, the second test, and the shape and all that stuff. Okay. The textbook has a set of guidelines that are pretty good to follow. So here are the sketching guidelines, steps. It suggests that we start by finding the domain of whatever function we're looking at. After that, we find the intercepts. And we'll go through examples and review each of these as we go through them. For now, let me just write down the big points that were suggested to follow. Domain, the intercepts, symmetry, if there's any of it, asymptotes. Of course, not all functions have those, but if they do, they're really helpful. Next, we'll find the increasing/decreasing intervals. And you remember, as soon as we know where the increasing/decreasing intervals are, we automatically know where the local max and min are. So these really are one step. Even though there are two major things there, it's really one step. Same thing with the next two. We look for concave upward or the concave downward intervals. And as soon as we have those, we automatically know where the inflection points are. Finally, using what we have found, primarily the points and the intervals, we can come up with a reasonably good sketch. When we sketch things this way, we are not looking for the perfect, accurate graph. We're looking for something that resembles what it should look like. Specifically, the shapes, the max, min, stuff like that. But we're not looking for the perfect graph. Okay, so let me put this on the other projector here. And we'll start with a relatively simple example. And we'll use that to review some of the steps that we haven't done in the past. Let's try to sketch x cubed minus 12x squared plus 36x. Okay, let's look at the domain. Starting with the domain, the first step that we are suggested to follow. Strictly speaking, not all of those steps are necessary, but they help. All right, let's start with domain. For this one, it's pretty simple. We know this is a polynomial. A polynomial has a domain that's all real numbers. It's always defined. So this really doesn't help us. We know it's going to exist everywhere for whatever value of x we can find. That's fine. Let's move on. We want to look for two types of intercepts. They tell us the points that are guaranteed to be on the graph. No matter what happens away from them, we know for sure, if they are intercepts, we know for sure those points will exist. To find x-intercept, we make y equal to 0, right? So you take your equation, 0 is equal to x cubed minus 12x squared plus 36x. Take an x out, and then you got a quadratic, which you can further factor. Minus 1236 is the perfect square. If all these three things multiply to be 0, then we know each of them has to be 0. So the x-intercepts are x is equal to 0 and x is equal to 6. Now we know at least 2 points on that graph, right? Whatever happens after that, we have other things to help us figure that out. There can be at most one y-intercept. You can have multiple x-intercepts, but there can be only at most one y-intercept. A function has to pass the vertical line test. If you have multiple y-intercepts, then it does not pass that test, right? There can be only one, at most one. To find out where that is, you make x equal to 0. So our equation becomes y is equal to 0, 0, 0. 0 cubed minus 12, 0 squared plus 36 times 0, and that's a 0. That tells us that our one and only y-intercept occurs at y equal to 0. This is actually the same point as x is equal to 0. So even though we have three things here, there are really 2 points, 2 unique points. That one's duplicating that. All right, so we got the intercepts. Symmetry. It's not always very useful, but occasionally you can use it to cut your work in half, essentially. Okay, now we haven't seen symmetry in a while, so let's review that. If you substitute negative x into your equation, the function here, and it turns out to be exactly the same as the function that you started with, so that's what it says here, f of negative x equal to negative f of x. This means that the function is even. And an even function has a y-axis symmetry. Whatever happens on one side of the y-axis happens on the other side. It's a mirror reflection. An example you want to think about, keep in mind, the one we've been looking at very often, x squared. That's a very, very simple example of something that has a y-axis symmetry. And you can see if I put in a negative x, I get exactly the same thing back. So this guy has a graph we know. Our little parabola. Whatever is on one side of the y-axis happens on the other side. Just a mirror reflection of that. If when you substitute negative x into your function, you end up getting negative of what you started with. This tells you your function is odd. An odd function, let me make this more clear, even function has y-axis symmetry. An odd function has what's called the origin symmetry. Whatever happens on one side of the origin happens on the other side. A very simple example to keep in mind is x cubed. If I substitute in negative x for x, then I get negative x cubed, which is negative of x cubed, and that's the negative of what I started with. When something has an origin symmetry, for this graph, it looks kind of like this. The point on one side of the origin goes on the other side. Exact duplication of that. Switches quadrant, if you want to think of it that way. It is also a simultaneous x and then y-axis symmetry. Two of those things happening at the same time. Okay, let's see what this function here has. Let's see if this thing has any kind of symmetry. Let's substitute in negative x in place of x. Change every single x you see to negative x. You see what comes out of it. Now compared to what you started with, this is clearly not what we started with. The signs don't match. Two of those are wrong. It is also not equal to the negative of what we started with. The negative of that is negative, positive, negative. I have negative, negative, negative. Doesn't fit. And this means that this thing has no symmetry. Okay, not terribly useful, but at least we ruled out any symmetry here. Moving on to asymptotes. You remember, vertical asymptotes happen when the denominator equal to 0, while the numerator is not equal to 0. If they're simultaneously 0, then that's an open circle. It's a whole in the graph. But if the denominator is 0 while the numerator is not, then that's where an asymptote can be. For the right horizontal asymptote, we take the limit to infinity. For the left, we take it to negative infinity. For the function we're looking at here, there's clearly no vertical asymptote. There's no way I can make the denominator 0. The denominator is a 1, right? There's no way I can make it equal to 0. So no vertical asymptote. For the horizontal ones, if I take x to infinity, then it goes to infinity. If I take x to negative infinity, then it goes to negative infinity. It's the leading term that's going to dominate. So whatever the leading term is doing, that's where the limit will be going for this one right here. If they are not numbers, they're not going to a 2 or 5 or whatever, but instead of going to infinity, then that means there are no horizontal asymptote. They just shoot up to infinity or negative infinity. It does not approach any number. For the function we're looking at, no vertical and no horizontal asymptote. That's okay. All right, so we covered the first 4. They're not always going to give you useful information, but they can help occasionally. I'll show you one example later where some of those things up front helps. Now the big ones, the second half of the guideline here, these are the most important things. Once you found these, you can get started very, very easily. Let's find the increasing, decreasing. We've done that before, so I'll go relatively quickly with those. Remember, increasing and decreasing deals with the first derivative. Make that equal to 0. Find the critical numbers. You can take out a 3 and then factor that. So we see x is equal to 2 or 6. That's also locations of potential max or min. We'll find out as soon as we find out the increasing, decreasing intervals. Okay, again, we've done this before, so I'm going to go pretty quickly with this stuff right here. Choose a number less than 2, plug into here, we get positive number. So increasing here, between 2 and 6, I'll choose a 3, and I get a negative number. Decreasing, and then choose something bigger than 6, 7, and I get increasing. So increasing here, decreasing here, and increasing. And automatically, the chart provides us with the locations of max and min. maximum occurs at x is equal to 2, right? Increasing before you get to 2, decreasing after you left 2. So max at 2. Let's find out the y that goes with it, because we want that point. That's one point we know is going to exist on the graph. It's a helpful starting location. So you take 2, go all the way back to the function there, plug it in, and you get 32. Okay, so this is a very, very useful information. It's a point that we know is going to be the highest point nearby that region. We got a minimum at x is equal to 6. The y that goes with that is f of 6, which turns out to be 0. Now you do repeat the steps with the second derivative to find concave up, down, and inflection points. Second derivative is very simple, 6x minus 24. Make that equal to 0. So x occurs at, there's a 4, 0 at 4. Do the same thing we've been doing with the first derivative. Find the sign of second derivative, left and right of it. And again, we've done this before, and it's a very simple function. You can go quickly with that. That interval should give us negative concave down. That interval is a happy interval, concave up. And then automatically, we know the inflection points. A sign change in the second derivative across here, that qualifies as an inflection point. So point occurs at 4, and y is f of 4. You always take the number back to the original function to find the y number, never any of the derivatives. You get 16. So the inflection point, IP, occurs at 4:16. Okay, so we walk through all the steps suggested to us. Now we sketch. You want to start with the points that we know. The points, these are the things I put in green. They're very, very important things to start. So the points are max, min, inflection point, and intercepts. These are things that we know they're guaranteed to exist on the graph. Everything between them, we can use the shape or the increasing, decreasing information to fill in the details. Let's start with what we got on this page. 6, 0 is a local minimum. Let's say it's right here. Now, I expect nothing to be lower than that in the nearby neighborhood of that point. And therefore, I expect some kind of bounce around like that. Let's go to a 2. The max is right here. 2, 32. That's our local max. I expect nothing to be higher than that in that neighborhood. Intercepts, I have a 0, 6. 6, I got it already. 0 is the point I haven't put on there yet. So here we go. This is my x comma y intercept. One more point, the inflection point, 4, 16, right here. The inflection point is not a local max or min. So things can be higher and lower or lower than that nearby. No problem there. Now we use, I would suggest the next thing you look at is the concave up or down. So then use concave upward or concave downward to fill in between. We only have one change here. Anything to the right of 4. So all the regions beyond here, this is going to be concave downward. I'm sorry, I got this backwards, didn't I? Concave upward, sorry. Second derivative is positive, is concave upward. Concave upward looks like a parabola opening up with the lowest point right here, so it doesn't take a whole lot of effort to realize we must have something that looks like that. Right? Concave up, local minimum. To the left of that, it's concave down. Concave down looks like a downward opening parabola. It has to start from here, go through that, get no higher than that, come back down. So again, shouldn't take a whole lot of convincing to see. We expect this kind of shape. It should be more curved. There, good enough. Okay? So there. So that's the graph of the function that we looked at. It's not the perfect graph, but we captured the shape information precisely right. We also captured the locations of max, min, intercepts, and all of that exactly right. Now exactly what happens after here, we know it's going to go up, but exactly how curvy it is, we don't have that information, but for this kind of sketch, we don't need that. All right, any question? Of course, like I said earlier, not all of these are necessary. Sometimes if you realize one of them if you find out one of them takes too long, it may not be worth the effort. Perhaps something else can give you the information that you don't really need to spend that time on. Okay. Say it again? Well, I had to show you how each one works, right? For the next few examples, we can go a little bit quicker with them. But that's the basic idea here. Any question? Does the process make sense? Okay, you all look awfully excited. No? Yeah, okay, I admit it's not terribly exciting, but you know what? It'll be on exam too. So if nothing else, that's gotta know enough to do that. All right, next example. Okay, so here we got x over x squared minus 16. I have a fraction here. Potentially, there's going to be some vertical asymptote somewhere. And you find out that those are actually very, very useful. Again, not all of these steps are strictly necessary. On WebAssign, they are necessary, but in practice, they are not strictly necessary. We can walk through some of these really quickly. Domain, obviously, cannot be 4 or negative 4, right? Now, here's where some shortcuts can actually help. Notice that when x is equal to 4 or negative 4, the denominator is 0, but the numerator is not. So that means these are also the vertical asymptotes. Okay, domain information can tell you the potential existence of vertical asymptotes. We'll get to them in a bit. Find out the intercepts. For x-intercepts, we make y equal to 0. So we get 0 equal to x over x squared minus 16. That means x has to be 0. Now we got 1 point, right? 1 point. Whatever happens, we know that point has to exist. There can be only one y-intercept at most. You find that by making y 0. I'm sorry, x equal to 0. Therefore, y is equal to 0 over 0 minus 16. That's, of course, it's 0. Therefore, the y-intercept is y equal to 0, which happens to be the same point again. These are the same location. 1 point. That's all we got so far. Symmetry. We change every single x we see to a negative x. And notice after we simplify the bottom a little bit, this turns out to be the negative of what we started with. Right? It's the negative of the original function. Okay, so what type of symmetry is this? Origin, right? No, that's not how you spell origin. Origin, there. Asymptotes. Let's start with the vertical ones first. The vertical asymptote, we already talked about it. They occur when the denominator is 0, while the numerator is not 0. So these are x is equal to 4 and x is equal to minus 4. How about the horizontal one? What happens when we take x to either infinities in this function? Zero, right? The bottom has higher number. So y equal to 0 is the horizontal asymptote. The x-axis, in other words, is the horizontal asymptote. Could it cross? It could cross. The graph is allowed to cross the horizontal asymptote, especially in the middle. This is the behavior when we go to infinities, right? It does not say anything about in the middle part of the graph. So it is allowed to cross. That's a good point, actually. Let me write that down. The graph can cross horizontal asymptote, but not vertical asymptote. It can never cross a vertical, but it can cross a horizontal. And like he pointed out, the x-intercepts are 0. That's also where eventually the horizontal asymptote would be. It is allowed to happen, just not the vertical asymptote. All right, next. Increasing, decreasing. We know how to take derivatives by now, so I'll just go ahead and write down the derivative of that. And it turns out to be negative x squared plus 16 over x squared minus 16 squared. Quotient rule. One step later, that's what you would get. F prime is equal to 0 never happens. Hey, that's not. All right, we're back. We're back. Don't touch that button. All right, so look at the top. If you want this to be 0, you want the top to be 0. The top is sum of two positive numbers. There's no way you can make the sum of two positive numbers 0. So this will never happen. However, we know f prime does not exist at plus or minus 4. We also know that these cannot be locations of max and min because they are the asymptotes. Even though ordinarily they have a chance to be max or min, here they cannot. There's no way they can be. The graph doesn't even exist at those places. Okay, make our chart here. F prime does not exist here, and let me write does not exist. Remember, these are also locations of the asymptotes. Let me write them down. It's always negative, yeah. Right. So? Yeah, we'll find out what that tells us in a little bit. You're right. It's always negative, and you can see that without even plugging any number, by the way. The denominator is forever positive. Anything squared is positive. If it's not 0, it's always positive. The numerator is always positive. This minus sign of an entirely positive quantity makes everything negative, no matter what you choose. It's forever negative. It's always decreasing, in other words. So there are no local max and min. And also, x is equal to plus or minus 4 are vertical asymptotes, therefore cannot be locations of max min. Okay, so far we don't really have much. We have asymptotes, we have 1 point, we know it's always decreasing, but no max or min. We'll carry on with the next step here. This is where we hope useful information can be obtained. That's our last chance. There's nothing more to do beyond that. Now we work with the second derivative. And again, we know how to take the derivatives by now, so I'll just go directly to what it is. And you get that by applying the quotient rule one more time. And you have to use the chain rule at some point to get to here. But simplified, that's what the second derivative will end up looking like. F double prime can be 0 when the numerator is 0. This thing here can never be 0. The only way we can make it 0 is when that's a 0. So that's the only potential location of that. F double prime does not exist at x is equal to plus or minus 4. And just like before, they cannot be where the inflection points are because the graph is not defined there. Now we check the sign. Does not exist, 0. Does not exist. Check signs. Minus here, checking here, you should end up getting concave down, concave up, down, and then finally up again. Down, up, down, up. It's right. Is something puzzling you though? Right. But this guy can change sign. A cube, right? It's a cube. It can change sign. Right. Good. Okay, so there are 3 sign switches, but only 1 inflection point because these 2 cannot be inflection points. Inflection points at x is equal to 0, and that happens at y equal to f of 0. You got to go all the way back to the first page to find what. Oh, there it is. We get 0. But not at x is equal to plus or minus 4 because they are vertical asymptotes and they're necessarily out of the domain. Okay, so we got shape here. This is always useful. Shape is always useful. The inflection point, this is not a new point, not terribly useful. Now we start with points as usual. And asymptotes. Asymptotes are very, very useful information. I only have one useful point. This is the inflection point and also the x and y intercepts. That's all I got right here. no other point available. I know for certain it's never going to cross the x-axis again. Never. And also we know that's the horizontal asymptote. Now let's go to the vertical asymptotes. They occur at plus or minus 4. Those are lines that the graph can never cross. And you know the behavior of vertical asymptotes. The graph is going to go to positive or negative infinity on either side of each one. Now, as usual, next we use the concave up, concave down information. It's far more useful than the increasing, decreasing, usually. This is usually all we need to do to figure out what's going on. All right, so let's start with between minus 4 and 0. Between here and here. It tells me it's concave upward. I have to start here, concave up, and shoot to, has to be infinity then to be concave up, right? So that's the only kind of possibility I can have. Half of it of an upward opening parabola, concave up, and sees the asymptote and follows it to infinity. Okay. Does that make sense, the way I reasoned that? Yes? No? Don't care? Okay. Between 0 and 4, concave down. So like a downward opening parabola sees the asymptote, shoots off to infinity, negative infinity. So there we go, concave down. I cannot cross that line, so I start a new part once I go to the right side of 4. Okay, now based on what we know, what should it look like to the right of the vertical asymptote at 4? What do you think? What should this look like? Decreasing, concave up, good, very good. So can you describe what it might look like? Okay, yeah. Decreasing, right? So it has to start high and eventually settles down. Will it cross the x-axis ever again? No, right? No, because we didn't find any more intercepts in the first step. And also we know, remember, this line right here is a horizontal asymptote. It tends to approach that. It may cross it, but usually not. So you can see, here's why it's always decreasing, right? Decreasing, and then concave up. The last part to the left of negative 4, concave down, and decreasing. Asymptote, asymptote. The asymptotes just kind of trap things, and things get attracted to them. So that shoots up to negative infinity, jumps back, decreasing again. And you can see there are no maximum or minimum. It's always decreasing. All right, that's it. Have a good weekend. See you Monday. Oh, okay, sure. I'll be in my office until 11. Oh, actually, probably 10:50 or so. When I'll be there.
And you're on the 8th floor?
8:48.
848. Okay.
Take the elevator up
To the 8th
and
floor.
then turn right.
Okay.
The second door